Hi everyone, welcome to tutorial 23 of our Introductory Python for Image Processing tutorial series. In this tutorial, I'm going to talk about reading proprietary microscope images into Python. In the previous tutorial, tutorial 22, we covered the topic of reading standard images like JPEGs and PNGs. So in this tutorial, I'm going to focus on reading proprietary images. And by proprietary images, I mean images with non-standard extensions like non-JPEGs. So TIFF, multi-dimensional TIFFs, in a way think of them as proprietary, although they're not proprietary to any specific vendor per se. But most microscope vendors or third-party software providers, they try to use different extensions or different file formats to contain these images or to display or to store your images. And there's a good reason for doing that, because these special formats allow maximum flexibility to play with the data during acquisition and post-processing. So for example, if you work with Zeiss microscopes, you're collecting images in .CCI formats. So let me go ahead and open a CCI image, starting with, let's go ahead and open our osteosarcoma image that we have been using in the last couple of tutorials. So here, as you can see, this is a color image and this is a color image. It looks like an RGB image, but this is not a JPEG, right? So if you open a JPEG image, then you would look, the image would look exactly the same, except in this case, I opened a TIFF image, and the same thing still holds true. So in this case, each pixel has a value for red, for green, and for blue. And a combination is giving us this RGB image. Now, if you look at this .CCI image, this image is a mixture of three different channels, okay? AF568, 488, and DAPI channels, okay? So, and you can turn these channels on and off, and you can work with this image right now, right? That now, if you want to do nuclei counting, this channel would be a great channel to extract and then perform your analysis. And this is exactly why proprietary formats exist, because now you have not only the data stored in the right format to get maximum out of the user interface, but also a lot of information is stored every time you modify something, that gets stored as form of metadata. So if you go down to info, for example, in ZenLight, you can see a lot of information about it, like what is the pixel size, what are the image dimensions. And pixel size is very important, because if you're trying to count your nuclei, or if you're trying to quantify the nuclei size, then this can be very important, right? To get real dimensions rather than number of pixels. And of course, a lot of information about the conditions under which these images are collected. So by the way, in case you wonder what software I'm using, if you're not a Zeiss user or also Zeiss user but never explored Zen, you can go ahead and Google search for Zeiss ZenLight. This is free software. Go ahead and download it. This is great for a lot of image processing tasks. I would say a lot of standard image processing tasks. And of course, you can purchase additional functionality like using machine learning based image segmentation and others if you think you need those functionalities, and add on to this. So going back, let's do pretty much the same operation. By the way, let me just show you one other image. Let's say, okay, I have a scratch essay image over here, and this is it's got a couple of channels. First, let's actually do adjust the brightness contrast, and you can see there is a GFP channel. I can turn it off, and I'm only looking at the TL image right here. And this is a time series image, and you can actually go through individual timestamps. So again, the whole point is the proprietary formats exist because it makes the user's experience easier when interacting with this user interface that's provided by the original manufacturer. In this case, I'm showing you the Zeiss interface. So now let's actually jump onto Spider and see how we can open a couple of these proprietary image formats. So now let's first revisit how we opened .jpegs and .tiffs. Again, let me go ahead and copy and paste the code so it's easy for us to focus. So reading standard images is very easy. For example, even regular TIFF files like the one I just showed you, which is just a two-dimensional RGB image. This is very easy. All you need to do is use either scikit-image or OpenCV to open these images. And I covered this in the last tutorial, so I'm not going to dwell too much time here. So all you're doing is io.imread and where path to your image, and do you want to read it as grayscale or as color? You can just say false here to read this as a color image. Okay, so let's run this line, and so you can actually see, okay, this image is a floating point with dimensions of 1104 by 1376. And I briefly talked in the last tutorial about how to convert images between floating to unsigned integers. So that's out of the scope for now. Now, same with importing using OpenCV. It should be pretty much the same, except the channels are flipped here. Instead of RGB, OpenCV reads images as BGR. That's the only difference. Okay, so this is our standard way of doing things. Now, before jumping on to CCI images, let's actually look at how to open non-standard TIFF files, because TIFF files can be multi-dimensional. You can have three-dimensional, you can have multi-channel TIFF files, although it's not highly common. So let me just go ahead and copy and paste these lines. And as you probably imagined, or to read proprietary images, you probably need to install some other libraries that enable you to read these proprietary images, which is exactly the case here. Okay, so for TIFF file, go ahead and pip install TIFF file. In fact, let's go ahead and let me comment that so you know how to do that. So here, pip install TIFF FILE, 3 F's in the middle. Okay. Once you install that, then it gets a bit straightforward. Then you just import TIFF file, just like you imported scikit-image or OpenCV, and then assign a variable img and tiffile.imread. Again, this is very similar to how we did in scikit-image, right? io.imread, and your image over there. So let's go ahead and I am picking osteosarcoma.tiff here. So let me clear all variables. So when we run this, we see only information from this image. So it says no module named TIFF file. So let's go ahead and pip install. Okay, so this is a great thing. So I haven't installed TIFF file on this system yet. So let me copy and then go ahead and paste it here and hit return. It says pip is not a standard command or something. So let me put exclamation mark, go ahead and paste it, and then let it install TIFF file. Okay, you'll go through these when you work with Spider. You'll realize that some libraries you have never installed, so you'll have to go ahead and install them. Okay, so there it is. It's ready. Now, hopefully this will run. So let's go ahead and run this one more time. Here you go, and now there you go, the image is up here. Okay, so now you can see that my image is 1104 by 1376 with 3 channels. This is exactly same as let's let me see if I can find the scikit image. This is exactly same as, yeah, let's go ahead and read image using scikit image, and as gray, let's make it false. Okay, so if we run this, let's call this image 2, so we can differentiate between these two. So if you run this again, you can see image and image 2 are exactly the same. Okay, so you can read TIFF files. Now, the advantage of using TIFF file, by the way, scikit image is actually using TIFF file in the backend when the extension is TIFF. Okay, please go ahead and look at the documentation for scikit image IO. You'll see exactly the same statement. Okay, it's using, when you read or write TIFF files, it's actually using TIFF file library in the backend. Now, but it's not actually doing advanced stuff. For example, if you want to look at, again, let me go ahead and clear the variable explorer over there. If you want to look at a TIFF file, for example, I have a TIFF file that's 3D nuclei. That's a 3D image. So it's not a multi-channel, but it's a 3D image. So if I go ahead and run this, so let's first go ahead and run these lines. So here it's printing our actual osteosarcoma image shape, and this is no surprise, right? It's 1104 1376 by 3. Now let me go ahead and run this one, 3D nuclei 8-bit. Okay, so if you look at this, let's go ahead and print the shape of image 1. Okay, so let's go ahead and print it, and you see it says 129 308 and 461. That 129 stands for 129 different images, and each image is a grayscale of size 308 by 461. Okay, that's what this is. So this 129 is the number of slices. Now I also have another image, scratch essay. I just showed you this image right here, this scratch essay. We have 2 channels here, and also we have different timestamps here. Okay, so how does that look like when you open it? When you open a TIFF. By the way, this is just a TIFF file, so I'm not sure if we have 2 channels, but let's go ahead and run it. Okay, so there you go. So now let's actually run image 2 and look at the shape down here. So now it says 10 by 2 by 289 by 400. 289 by 400. Again, let's go back to our Zen. 289 by 400 is the size of this image. And then we have 10 time series, timestamps. And then you have 2 channels, TL and GFP. So that's how you can read proprietary images. And again, TIFF files are not really proprietary. So let's actually cover the topic of opening CCI images. There are a few libraries out there. And again, your best friend in this case is Google search. Google search for how to open, for example, CCI images in Python, and then you'll find the right resources. But let me just, since I already did this, let's go ahead and copy and paste it here. So the way you read this is, let me also copy this line. So the way you read this is import CCI file. I think if I run this line, it basically says, okay, no module name CCI file. Again, I deleted the library so I can show you how it looks like when you run it. This is not one of the standard libraries. So again, we'll do the same thing. So pip install CCI file. So it should install it, and then when we run it, it should go ahead and run it. Okay, so now let's go ahead and run this line. It worked fine. So now let's read the CCI file again, just like any other libraries. It's once you import it, it's CCI file.imread. Okay, and then we are going to read this image, osteosarcoma 01.cci. This is exactly the image we saw here. Okay, it should have these 3 channels, and the third one being the DAPI channel. So now let's go back and print the image shape so you can see exactly what the shape looks like. So this is 1 by 1 by 3, 1104, 1376, and 1. How come we have so many different things? Let me copy and paste one more line here so you can see what this stands for. So the first one stands for time series. In this case, we only have 1 time stamp, right? The second one is number of scenes. For example, if you have Cell Discoverer, you can have multiple scenes when you collect your images, okay, if you have a CD7. So that would be the number of scenes. In this example, again, we have only 1 scene. Channels is number of channels. We have 3 channels here, red, green, and blue. And Y, X, and Z. So we have our Y is 1104. Sorry, I mistakenly said red, green, and blue. The 3 channels stands for the 3 channels we see here, 568, 488, and DAPI channels. Okay, so these are the 3 channels that we have, and Y, X, Z, and the last one is RGB. So here we only have 1. Each image is a black and white, I mean a grayscale image, I should say, because when you turn this off, yes, it looks in like blue because that's artificially colored in blue. Okay, the image itself, you're actually collecting grayscale images and then you're applying this color. So that's why it actually says 1 for your RGB. Now let's open one more image to get a bit more clarity on this. So let's go back to this scratch essay image, which is this second image that I opened here. Okay, this is the scratch essay image. Now, how does that look like when you open? So let's run these lines again. So here you have 10, right? 10 timestamps and 2 channels. I mean, 2 series. Sometimes these channels, I guess I missed the scenes and channels here, and then 1 scene, and your image is 400 by 289, and RGB is just 1. There is no red, green, and blue. It's just a grayscale. Okay, so that's how you can read proprietary images. And let's go back to our original image and let me show you. Okay, so yeah, we read this, but this is not a standard type of image. So what can we do once you read it, right? So let's actually extract the blue channel or separate the channels red, green, and blue. So the way you do that is, first of all, let me go ahead and copy these lines. So Okay, there you go. So when you extract only relevant pixels, right? So now what am I doing here by extracting this? So we have this specific image is 1 by 1 by 3, 104, 1376, and 1. So I don't care about these two ones. Like I don't care about time series and scenes. I don't care about RGB. All I care about is number of channels, X, Y, and Z. So I'm saying, okay, don't get anything from channels or scenes. Don't get anything from my RGB and extract only the ones from here. So if you run these lines, then you can see that our image is now 3 by 1104 by 1376. You can rotate, you can change these axes and all that. So once you read the image, then now it's up to using NumPy to manipulate your numbers. So to extract each channel, we know that channel number 0 is the first one, right? Which is red. Channel number 1 is the green. Channel number 2 is the blue. So that's exactly what we are doing here. So just so we take our image 1, and I'm saying, okay, my image 2 is image 1, where the values are all the values for X and Y, but only the values coming from the first channel, which is represented by 0. That's what this is. Again, please try this a few times so you get a bit comfortable with NumPy. We covered this as part of our NumPy tutorial. So when I run this, now you can see my image 4. If you go up here, each of these image 2, 3, and 4 are the same dimensions. Okay, unsigned integers. Now I can go ahead and plot them. Again, I'll record a separate video in terms of how to display images on screen, but for now, just trust this code for plotting. So all I'm plotting here is just image 2, image 3, and image 4 as separate images. So we can actually have a look at these images here, and you can now see I'm plotting everything in red, because I mean, you can actually plot each image in different color, but they're all grayscale images. So this is my red channel, this is the green channel, and this is the blue channel. So if your goal is to read in a CCI image and extract the DAPI channel and do some sort of a nuclei counting, then all you got to do is at this point just take your image 4, which is our DAPI channel image, and continue with the process. Okay, so this explains CCI images again, because we know CCI images well at Zeiss. But if you have other proprietary images that you want to work with, then please go ahead and Google search for these other proprietary images, image formats. I'm pretty sure you'll find a library that can help you read the images. And some are easier, like CCI, working with them in Python is very easy because I've put in a lot of effort to enable that. And some you may find it a bit difficult, but please look at the documentation if you need more help. And you can also read images, for example, omitive images. Okay, these are the ones from bioformats. So you can read almost all any type of proprietary image, and I hope you learned something useful here, especially how to import CCI images and how to work with them in Python. So thank you very much. And in the next tutorial, I'm going to talk about how to visualize these images. I mean, we had a quick look here, but let's actually look at how to visualize these images in Python, at least a couple of different ways. So thank you very much, and let's meet in the next tutorial.